Morning, everybody. Happy President's Day. And today we're going to try to do two sections. The first one's graphing polynomial functions, and the next one will be 4.3. It'll be the properties of rational functions. All right, so to begin with, when graphing a polynomial function, we need to know certain things. The degree of the polynomial. The degree is the largest exponent. The degree of the polynomial is going to tell us a couple things. The shape of the curve, the direction, whether it's increasing or decreasing, as long as we have the leading coefficient also. We'll go over that in a second. It'll tell us the maximum number of x-intercepts the maximum number of what are called turning points in calculus. We call those points of inflection. Where the curve stops going down and starts going up. At that point is the point of inflection. The maximum number of vertices. That's often the degree. The degree is the largest exponent. So the second thing we need to know, the intercepts. The x-intercepts and the y-intercepts. Set y equal to 0, set x equal to 0. The multiplicity of each intercept once factored. And let's see what else. Yeah. Some points on the curve. All right, to begin with, let's look at what we mean when we say direction and shape. polynomial has this shape, this format. The the first term is called the leading term. The leading term is very important. The exponent of it is called the degree, and the coefficient is called the leading coefficient. The shape and direction of the polynomial can be estimated with the leading term. We look at what's called the end behavior. The directions of both ends of the graph. So this is how we're going to do it. These will be the degrees, and these will be the leading coefficients. If the leading coefficient is positive or if it's negative. If the degree is even versus if it's odd. This is just looking at the end behavior. So if it's positive and it's even, then both ends will be pointing up. What happens in the middle, we don't know. So from our first and last intercepts, the graph will be doing that. If n is odd, well, let's just say if n is even and a is negative, our graph will be pointing down. So if a is positive, it's increasing. If a is negative, it's decreasing. If n is odd, both ends point opposite directions. It's an increasing function because a is positive. It will be going up to the right. And if a is negative, it's a decreasing function. So this will give us the basic shape of the graph. Just by looking at the leading term. A couple of other things it will tell us. If the degree n, if n is even. Three, four, five, six. We can have at most n x-intercepts. And at least 0 x-intercepts. So let's see an example. Let's look at the x squared possibilities. It's even. So we know both ends point the same direction. It could look like this. It could look like this. And it could look like this. We have two solutions. One solution or no solutions. Actually, no real solutions. If it's like this, your answers will be imaginary. If n is odd, one, two, three, 6, 7. Ooh. We can have at most n x-intercepts. And at least one x-intercept. Because they're pointing opposite direction. One of these directions has to cross the x-intercept, x-axis. Note, as we go on, the x-intercepts will also be called solutions. Right, and they're also going to be the factors, the zeros of a polynomial. So those terms I'll use interchangeably. All right, so let's look at this. If you have a final factored form like this of your polynomial, these exponents are called multiplicities. It tells us the number of times that 0 is repeated. For example, if we graphed y equals x squared, we'll get this as an answer. We're supposed to have two answers, and they're both going to be 0. So that's what it tells us. The sum of the multiplicities equals the degree of the polynomial. So in this example, the degree is 8. 5 plus 2 plus 1. There's an invisible 1 there. So what good are the degrees? Well, I mean, the multiplicities? Well, first off, we know what the zeros are. Each factor set it equal to 0 to find the x-intercepts. So I have x plus 2 equals 0, x equals -2. X minus 3 equals 0, so x equals 3. And x plus 4 equals 0, so x equals -4. Since the degree is 8, and all the x's are positive coefficients, that means, so we know that a is positive, and n equals 8. So our graph will look something like this. So from the endpoints, our graph does that. If the multiplicity is even, the graph bounces off that x-intercept. As in this point, x squared, it just bounces at 0. If it is odd, the graph crosses at that x-intercept. So what do we see here? At -4, the multiplicity is 5, so it means it crosses. At -2, it's 1, so it crosses again. At 3, it's 2, so it bounces. So somewhere along the path here, we'll have a y-intercept. That's what the graph's going to look like. Now, to find the y-intercept, set each x equal to 0. So we have x plus 2, x minus 3, x plus 4. So we set all the x's equal to 0. So we have 2, -3 squared, 4 to the 5th. and whatever that's gonna be. It's 9 times 2 is 18 times 4 to the 5th. That's what my y-intercept's gonna be. All right, and then once you find that, you plot some points, and then that'll help you through it. All right, the next section, next two sections of this chapter, next two parts of this section deal with using calculators or any type of technology you want to. You can use any technology you want to graph these equations. Some people like to use their cell phones. Some people like to use calculators. Some people use their computers, like Desmos is whatever you want to use. And yeah, that's all there is in this section, because I'm not too crazy about using technology to do anything other than checking my work, not doing the work for you. All right, so that does it for section 2 of chapter 4. Stop this one so I can start the next video.